Hello, friends. This is Professor Sarvesh Varjurkar. Uh, Today, we are here for the AICT sponsored Prerna scheme for SCST candidate for Ballarpur Institute of Technology, Ballarpur, for Computer Science and Engineering branch, related and IT, Computer Science and Engineering, and along with IT branch, for the subject Computer Architecture and Organization, with the topic Instruction Pipeline and Pipelining Hazards. This is our eighth lecture. Okay. In the today's session, I'm going to deliver you about the various points which we are going to discuss it today. This is the outline for my today's presentation related to the basics of pipeline, what is pipelining, pipelining principles, along with risk and its various five-stage pipeline as well. Part 2 belongs to some challenges like pipeline hazards or structural hazard. We can also going into the deep in matter related to data hazards as well, along with the control hazards as well. Next is, first of all, we'll go with the pipelining first. What is pipelining and how it works? This is, as we are already known that, I mean, everybody is very much aware about what is pipeline. Pipeline is nothing but the execution when there is a when there is a way in which we are going to execute any command, along with that this pipeline may works. Try the laundry example. Whenever an instruction pipeline reads consecutive instructions from memory, while in the another segment the previous instructions are being implemented, ultimately pipeline processing appears both in the data flow and the instruction field as well. Again, we'll go with that laundry example in the upcoming slide. Yes, look like this. See, A, B, C, and D. Say Anne, Bran, then Kathy, and Dave. Each has one load of clothes to wash, dry, and to fold. See, again, pipelining means unless and until you wash, you don't make it dry. Unless and until you make it dry, you don't make it fold. After the complete washing, you can go with the next step, that is dry. Till then, your dry and fold is in pipeline. For example, say washer, it takes 30 minutes to wash. Dryer, it takes 40 minutes to dry. And folders, I mean the machine which gets fold to the clothes will take 20 minutes. In that way, all these three steps requires summation, I mean requires combinedly 1 hour 30 minutes, or I can say 90 minutes. There is one possible more event associated with such design is that instruction can generate a branch out of sequence. See, as if this is a sequence. Firstly, you will go with the wash, then dry, and then fold. Accordingly, unless and until you can generate the sequence, branch out a sequence, your steps will not get executed. In this method, the pipeline is clear and all the instructions have previously been read. Whatever the instruction given by the washer, the clothes have to follow. Whatever the instruction given by the dryer, again it have to follow, and folder, again it may have to follow. Likewise, sequential laundry, A, B, C, D. These are the four orders. I mean the task order. It took 30, 40, and 20 minutes respectively for washing, drying, and folding. B, again it requires 30, 40, 20 minutes. C, first of all, the execution task is completed for A. Then it will, or I can say Anne, Anne, and then I can say it may be completed for Bran, and then Kathy, and then Dave. All these four may get executed. Same thing for C as well, and for D as well. The whole system works in this particular sequence for all the given inputs which are already been given by the task order. A computer can be constructed to support a two-segment unit with an instruction fetch unit and instruction execution unit, which we have already seen it in the last video. Using a, yes, what matters, which path, which sequence it follows the queue property, the property of the queue. As we know that the property of the queue is nothing but first in, first out. Whatever the instruction which comes first, whatever the task which come first will be get executed first. First, second, third, and then fourth. That means first in, first out. That buffer the instruction for fetching the segment is implemented. This is a normal method of unit forming a queue instead of a stack. When the implementation unit is not creating a memory, the control increments it controls in the control increments the program counter, and that helps its address value to read consecutive instructions from the given memory. Whatever the given memory, whatever the instructions already there in the given memory, it should read in that consecutive instructions from the given memory. Ultimately, as we know that for each task or for each person, it requires 1 hour 30 minutes. So for all the others, in the sequential laundry way, it requires for 4, it requires complete 6 hours. What would you do to reduce the time? What you do, you can do like this to save the time. You can change the position, see, of if the dryer parts comes, if the dryer parts executes at the first, for the first task order, you can then engage the second task by giving the dryer to them, sorry, by giving the washer to them. After the first washer completed, the second washer immediately starts. It may not wait for the remaining dryer and the folder part to execute the second instruction. No, you can do this particular technique, so that a, after the completion of washing of A, you may directly start the washing of B. In that case, it can save your 60 minutes. Same thing, same thing, you can go with the dryer part as well. Immediately after the dryer, so immediately after the washer, you can dry your system, you can dry your clothes like this. It can again be shifted, or I can say it can be preponed. It can be preponed. It reduce your time. See, the whole time it requires 30, 40, and 20 minutes, but you can change the order, you can change the sequence in that particular manner. If you work in this manner, your execution will take complete this much time. That means 3 or 5 minutes. Ultimately, you have reduced. Ultimately, you have reduced 2.5 hours. 2 hours 30 minutes is around 150 minutes exactly. This is a method of unit forming a queue instead of a stack, as I have already discussed. When the implementation unit is not creating a memory, the program counter and helps the address value to read the consecutive instructions from the given memory. Consecutive instructions matters a lot, since the consecutive instructions are working into the play. It can automatically reduce your the time required for the complete execution. Observation. What are the various observations that we have observed over here? The observations are like a task has a series of stages. Stage dependency is like wash before dry, dry before fold. Multitask with overlapping stages is occurs. Simultaneously, we use different sources to speed up. It can slows the stage that determines the finish time. It can slow the stage that determines the finish time as well. Look like this. In the first box, it requires around this much amount of time, but in the second vertical box, it again requires this particular thing, so that 40 so that dryer took sorry folder took 20 minutes, dryer took 40 minutes, and washer took 30 minutes. In that case, if you go through the particular sequence, no speed up for every individual, for any individual task. A still takes, see, A still takes 90 minutes, 30, 40, and 40. Sorry, 30, 40, and 20. 90 minutes, that is 1 hour 30 minutes. But speed for the average task time it executes, for example, it is like 3.5. 3.5 is the complete task that we require for the complete execution of the whole process, including all the tasks, task number A, B, task order A, B, C, and D. In that case, 3.5 multiplied by 60 divided by 4, it is equal to 52.5, which is less than a single task, which the time which is required for single task is 90, whereas at the average I can get it 52.5, which is less than 90. In that case, this is simple assembly line, I can definitely say, with the help of this particular example. Unless and until if you pack a particular automation for a car, everything is in pipeline. Every robotic arm over there is simply for his own task itself. Or you can see the example of this Coca-Cola bottle. Firstly, the raw bottle will be there. Then it can enter, it can fill it. We can pour the liquid or the material in it. Then we can fill the gas inside that liquid. Along with that, you can then go with the stickers and then the uh, knob of that bottle, the cap of that bottle. The whole sequence is like this. This is particularly called as the assembly line program. And this whole concept is called as the pipeline. Now, now we'll go with the second part, that is pipelining principles. How it works and how it used. An implementation technique whereby multiple instructions are overlap in its execution. For example, say B wash while A dry. Look at this. Look at this. B is washing while A is drying. That saves your time. It directly means that your washing get 30, 30, 30, 30 minutes sequentially. Your washing gets 30, 30, 30, 30 minutes sequentially. The whole process, no delay is there. The whole process may get solved in 120 minutes itself. The whole washing, it requires only 120 minutes. 30 multiplied by 4. In the same way, like this. The example I have given over here. What is the essence of this? That start executing one instruction before completing the previous one. If you are waiting for the previous one to complete the whole task of the previous instruction or the previous task, it may not execute fully. What is the significance of this? This makes your CPU fast. That makes your CPU very much fast. That equals the length of pipe. That means the balanced pipeline is another way, where example wash, dry, and fold in 40 minutes. Per unpipelined laundry time, it requires 40 multiplied by 3, because 3 pipe stages are there. You can wash, dry, and fold sequentially. It can require only 40 minutes for all the performing tasks, like this: AA, BB, and AB. Sorry, CBA and DCB. One task per instruction per 40 minutes. It can automatically reduce the performance. It can automatically increase the performance. That means the time per instruction by pipeline is equal to time per instruction on unpipelined machine upon number of pipe stages. Whatever the number of stages are there, it is up on that. So speed, as we know that speed up by the pipeline is equal to the number of pipe stages. Whatever the number of stages are there, all have to get executed with a particular sequence which is given to you already. The various stages are, as we have already discussed, first is washing, then drying, and then folding. What is the terminologies that we are going to use in the pipelining? First is latency, the time of an instructions to complete. Throughput of a CPU, that means the number of instructions completed per second. And then the clock cycle, where everything in CPU moves in lockstep, which is synchronized by the clock. Processor cycle, it is the time required between, of course, the complete cycle, it is the processor cycle between the moving instruction one step down the pipeline. It directly means that for every stage, that is the time required to complete a pipe stage, which is maximum time, which is for completing all the stages. Along with that, one or two clock cycles, but it is rarely more. And CPI, that means clock cycles per instruction. Whatever the cycle instructions require, whatever the time required or cycles required, clock cycles per instruction is there. The buffer facilitates a queue which is from the regulate, then derive the instructions for the implementation unit. Of course, wherever the implementation unit is there, it requires certain amount of clock cycles per instructions over there. A device which complex instructions, of course, if any of the device gives you the complex instructions that needed other steps in addition while fetching and execute to the process and instructions thoroughly. In this method, the device requires to process each instruction with the various steps. I can definitely instruct some steps over here. It can fetch the instruction from the memory. It can decode the instruction, or it may, calculate effective addresses as well. That we have studied it in the last video. This is all about the pipelining principle, and then we'll go with the risk and its 5 stages pipeline. We'll go with that. What is risk? As we know that risk, the full form of risk is reduced instruction set compute. As the name indicates reduced, as the name indicates reduce, what it matters? It can reduce the instruction set. All operation on data apply to the data in registers and typically change the entire register. For example, say 32 or 64 bits per register, you can change the complete or entire register over there. Only load and store operations affects the memory. These are the properties of risk. Load and store operations affects the memory, where load is equal to move data from memory to register, and store is equal to move, of course, as these are the principle, or these are the properties of risk, where the load is equal to move data from memory to register, and store is equal to move data from register to memory. Only a few instruction format, all instructions typically being of one size. Of course, if to avoid the inconvenience, it is of one size. All the instructions are of same size. Yesterday we have gone, sorry, in the last video we have gone through an example. For example, say if 32 bits word is there, we have divided it into 4 different parts of 8 bits each. Directly means 4 parts of 8 bits each of equal size. We have distributed it in the equal size. Next is, if 32 registers, 3 class of instruction 1 will go with that arithmetic logic unit instructions. Along with that, operate of 2 registers or a register plus extended sign, or sign extended, that means immediate store, that store the result into the third register. That addition, it means we can add any element, and subtract, it means you can subtract any element as a register, third register. And along with the logical operation, that means it may be and, it may be or it may be any kind of thing. It can fetch the operands from the memory also. It can also execute the instruction, and it can save the result in suitable place along with that. Next is the 3 classes of instruction. Again, the load that stands for LD, and store that stands for SD. For the instruction, that base register plus offset is there. The sum called effective address is used as a memory address. Effective address is used as a memory address over there. Along with that load, which is used a second register operand, as the destination for the data which is loaded from the memory, and store is used as a second register operand as a source of the data. See, store is the source of the data and load is the destination for the data. that stored the data into the memory and that loaded the data from the memory. That's why it is called as load, and that's why it is called as store, respectively. See, multiple segments can take different time duration to work on the incoming data. Along with that, this can avoid the instruction pipeline from working at its maximum speed. Few segments are skipped from the specific operations, of course. It may be at the loading and at the load stage or at the store stage as well. Next is branching. See, three classes of instruction three are like this. Branching again plays a very important role. Like segment, as we have already discussed, segment one, segment two. Segment one can fetch the instruction from the memory. Segment two can decode the instruction and calculate effective addresses, and then we'll go with the branch. See, branch is in terms of C or in terms of flowchart, I can say it is a decision box in which branch or in which way it may go, that can be decided by that branch. Branches and jumps, that conditional transfers. If the conditions satisfy everything, it will go to the next step. If the conditions are unable to satisfy everything, it will go to the previous step. Branch, that specify the branch condition with a set of condition bits, or comparison between two resistors or between a resistor and a zero, that can decide the branch destination by adding a sign extended offset to the current program counter, as we have seen it in the previous video. What is the risk? Again we'll go with the at most 5 clock cycle per instruction. For example, see, IF, ID, EX, memory, and WB. These are the 5 clock cycles, and we'll go with in a particular way of instruction fetching first, then send to the PC memory, and then fetch the current instruction from memory. And PC is equal to PC plus 4, and then each instruction is of 4 bytes. Each instruction is of 4 bytes of equal size. I repeat, for equal size. Next is instruction decoder, that is ID. Instruction fetch is IF. EX stands for execution, MEM stands for memory, and WB stands for write back cycles. We'll go with that instruction decode first. Second, the instruction decode, that or register fetch cycle, that decode the instruction, that can read the registers which is corresponding to the register, that source corresponding to the register, or I can say that source specifiers, where execution or effective address cycles comes into the play after the instruction decoder, where arithmetic logic unit operates the operand from the ID, that is instruction decoder. Three functions depending on the instruction type. One, that is memory reference, that where arithmetic logic unit adds base register and offset to form a effective address. As we can already discuss it in the previous part, where the segment, that instruction fetch from memory is decoded in the second segment, and the effective address is computed in the independent arithmetic circuit, or I can say arithmetic logic unit as well. Of course, the instruction fetch segment can be executed with using again the property of queue, that is first in first out, or I can say that buffer as well. That arithmetic logic unit performs the operation by opcode on the values read from the register file, and arithmetic logic units also operates on the operands on from instruction decode, where register immediate arithmetic logic unit instruction operates on the first value, as if we know that it follows the first in first out property. Whatever the value which comes first can be get executed first, which can register the file and sign extended then immediately, like this. The fourth way or the fourth segment is like the memory, where you can access the memory, or memory access will be there for load instruction. The memory does not read using the effective addresses. First, for store instruction, the memory writes the data from the second register using the effective addresses. An operand from the memory is fetched in the third segment. Operand from the memory is fetched in this segment, where where you can go with any different operand. It may be addition, it may be subtraction, it may be deletion, or whatever it may be. Next is write back cycle, where for register arithmetic logic unit or load instruction, or you can write the result into the register file, whether it comes from the memory or where it comes from the arithmetic logic unit as well. All this can sequentially executed 5 clock cycles per instruction for every particular way, like this: IFID, IEXMEM, and write back after exactly exact stage, like the pipeline that uh, uh, we already have seen the same example in the laundry, as a laundry example. Simply start a new instruction on each clock cycle. The speed up is equal to 5. It can automatically saves the time. Instruction I, it requires the clock number till 1 to 5. Instruction I plus 1, it is incremented by I from 2 to 6. Instruction I plus 2, 3 to 7, I plus 3, 4 to 8, and I plus 4, it is 5 to 9, like this. The speed up, we can say, we can reduce, is equal to 5 itself, like this. 5 stage pipeline, again with the help of the diagrammatic representation. How it works, and I have already explained it in this slide, where the separate instruction and data memories to eliminate conflicts for a single memory between the instruction fetch and the data memory spaces over there, where instruction memory, register, arithmetic logic unit, and then data memory, and then register again. It is simply like this. The execution is from left to right itself. It can also use the register file in 2 stages, either with half it may be clock cycle, either with half clock cycle or in 1 clock cycle right before the read. Yes. In the next slides, I am going to explain you about what is the right before read and what are the various hazards that occurs in terms of the execution or the pipelining, complete pipelining procedure. How it works, it can again introduce the pipeline register between the successive stages. Whatever the sequence of the stages occurs, it can execute, it can introduce the pipeline register between that successive stages. Pipeline register stores the result of a stage and use them as an input of the next stage. Along with that, it can execute all the instructions sequentially. Meanwhile, it can save the time as well. 5 stage pipeline, the diagrammatic representation or diagrammatic working is executed, is given over here. Again, it saves your whole time. Just now, the same example in clock cycles, but the time required in clock cycle, it from uh, clock cycle CC1, CC2, CC3, CC4, 5, 6, 7, and 8, 9. Meanwhile, the first instruction, it requires from CC1 to CC5. Second is from I plus 1, that is CC2 to CC6. Third is from CC3 to CC7. Fourth is from CC4 to CC8. And fifth is from CC5 to CC9. It can consider an unpiped instruction of 1 clock cycle, 4 clock cycle for arithmetic logic unit and various branches, 5 cycle for memory operations, which is relative frequency of 40%, 20%, and 40%. If 0.2 ns pipeline overhead, it is the example due to some sort of majority of the times it may occur, many of the time it may occur due to stage imbalance or pipeline register setup, or we can say that clock skew also operates over there. How much speed up by pipeline? That maybe the question arises. It can go in a particular direction with this particular formula. Speed up by pipeline is equal to average instruction time per unpipeline upon average instruction time pipeline. By using this, you can definitely able to calculate the answer. And this is all about say 3.7 times. That is the answer. Next question arises that when pipeline is stuck, if any particular instruction set does not execute a given instruction for a given for a given instruction set, in that case it may occur the stuck. Your pipeline instruction may not get executed due to some or other reason. You have to stop over there, or you should be your your uh, your complete output or your complete execution will not be get outside. Next, we'll go with the part two of this today's class, where the hazards, various hazards that may occur in the pipeline at the time of pipeline process. First of all, we'll go with the various types of conflicts that may occur in the pipelining, and then we'll move in that direction again. Pipelining, as we are aware about the whole concept of pipelining now, I can summarize it within 5 to 5 minutes. Like this, pipelining is a technique of breaking a sequential process into small fragments or sub operations, where the execution of each of these sub procedure that takes place in a certain dedicated segment that function together with all other segments. Then there are three types of pipelining conflicts, as we have already gone through. First is resource conflict, where these conflicts arises due to insufficient resources, wherein it is not possible to overlap the operations. The performance of pipeline processor depends on either of two conditions, that may be whether or not the functional units are pipeline, or do the execution units, multiple execution units that allows the available mixture of instructions of a pipeline. If a particular combination the pipeline is if a particular combination that pipeline is stalled to avoid resource conflicts, then there is a structural hazard. We'll go with that hazards as well. So, or second one is data dependency conflicts, where these conflicts arises when the instructions in the pipeline depends on the result of the previous instruction. Like this, if which is on the screen, if the first instruction, if the second instruction is depend on the first, unless and until your first instruction may get executed, the second instruction may get stuck. I say one followed by two, unless and until one get completed, the second will not get executed. That may another conflict. And third one is the branch difficulties, where the difficulties is faced when the branch and other instructions change the contents of the program counter. Then there is no then there are two different kind of branches, such as conditional and unconditional. That unconditional branch always causes branching, that difficulties in terms of control hazard, where the control, it can operate while critical situations may be there. Along with that, if your the whole working structure is in a particular proper way, it may not occur different hazards to you any different hazards to you. The upcoming slides, I'm going to explain about the whole these things. That means the structural hazard, data hazard, and control hazard. First is pipelining hazard. I will go with each and every one in a sequential manner. Whatever the root cause, whatever the solutions of that branch hazard, or data hazard, or control hazard, I will explain it in a simple way to you all in terms of the various hazards. Okay. Firstly, we'll go with that structural hazard. What are the root cause, how it occurs, what are the conflicts, how it occurs, and so on. What is the solution for that as well? Firstly, root cause of structural hazard is resource conflicts. As I have already explained the resource conflicts just now, where the resource conflicts occurs arises due to insufficient resources. I repeat, due to insufficient resources, wherein it is not possible to overlap the operations. Whatever the operations are, it is not possible to overlap the operations again and again. The performance of pipeline processor depends on whether either of the two conditions are follows. There are two different conditions. Before going to the solution, I'm going to explain that two conditions. Whether or not the functional units are pipeline, that is the first condition. You need to check the functional units are pipelined or not. Do the multiple execution units allow all the available mixture of instructions in the pipeline? If for a particular combination the pipeline is installed, or I can say it is stalled over there to avoid the resource conflicts, then there is a structural hazard. A processor with one register write port but intend two writes in CC, as if the processor with one register, how can it write two? It can cause a hazard. The given for that, we can give you one solution. We can install or stall one of the instructions until required until required unit is available. Unless and until required unit is available, we may not go with the process. So we may not execute the process rather, and in that case the structural hazard may occur. The structural hazard occurs if two instructions need help of a given hardware resource at an equal time, at the same time. The most common situation in which the hazard occurs is when the resource request for the memory. Consider a situation when I can give one example. Consider a situation like this. Consider a situation where one instruction need to access the memory for storage of the result, and while another instruction is being fetched. See, first instruction is needs to access the memory for storage of the result, while the another instruction is being fetched. Instruction 2 is getting out, that means instruction I plus 1 is getting out, but first instruction is need access to the memory. In that case, if the instruction and the data reside in the same cache unit, only one instruction can proceed and another instruction is delayed. To avoid this, we have one solution. To avoid this conflict, many processors use separate cache memory or separate cache for instruction and the data. If you are going to use separate cache memory for instruction and the data, the conflict may not occur. One memory port, memory conflict, data access versus instruction fetch. That means memory it requires separate, and for instruction fetch it again requires separate instruction over there, like this. Which the part which is given in that red box is exactly same as like this. Yes, it requires, for example, say load instruction, instruction fetch, instruction decode, execution, memory, and write back. I plus 1 it requires from 2 to 5. I plus 2 it requires 3 to say 3 to or 3 onwards. And for I3 we can go with that stall first. We can wait for that to avoid the hazard. Install instruction I plus 3 till CC 5. In that case, say ideal CPI is 1. That means the clock cycles per instruction. 40% data references, that can gives you the structural hazard with 1.05 times higher clock rate than the ideal. The question arises in that case, is the pipeline with or without hazard, which one is the faster? The answer is by how much? See, the answer is very simple. The average instruction time, many of the times the question asked in this particular way. The given data, 40% data references is given to you, structural hazard with 1.05 times the higher clock rate than the ideal, and you have to answer, is pipeline with or without hazard faster by how much time or by how much clock cycles? The answer is average instruction time without hazard is equal to the cycles per instruction multiplied by clock cycle time, which is the given one, which is the ideal one, I can say. 1 multiplied by clock cycle time, which is ideal, and the average of that is average instruction time with hazard is equal to 1 plus 0.4 multiplied by 1, cause 40% is already given to you, the clock cycle time, multiplied by clock cycle time, which is ideal, upon 1.05, since you have to calculate it for 1.05 minutes. So is equal to 1.0x clock multiplied by clock cycle time, which is the ideal one. So without hazard, it is 1.3 times faster. I can say that without hazard, the structure, without hazard, it is 1.3 times faster than the with hazard time. This is all up to the data, all about the structural hazard. Second one, will go with the data hazard or the data dependency. What is data hazard? How it occurs? Look at the matter. Firstly, the data dependency, which in which that is the root cause of the data hazard. Unless and if you are dependent on the previous instruction or the execution of the previous instruction, you may not proceed further. May not proceed further. In that case, when the pipeline changes the order of read oblique write access to the operands, the root, that is the main root cause of this data hazard. Where these conflicts or this hazard can arise is when the instruction in the pipeline depends on the result of the previous instruction, as I have just now discussed. Unless and until if it depends on the previous instruction, if it not may if it not may executes the previous instruction, you may not execute or you may not fetch the second instruction. In that case, the data dependency or these conflicts or this data hazard may occur. These instructions are still in the pipeline and not get executed yet. When either the source or the destination operand of an instruction is not available at that expected time in the pipeline is stalled. In that case, such situation is termed as data hazard, or I can say it called as data conflict. So that the order differs from the order which seen over there by sequentially executing the instruction or an unpipelined processor. Consider a program. In the next slide, I am going to give the example. Consider this particular program with two instructions, say I1 and I2, I1 followed by I2. When the program is executed in the pipeline, the execution of these two instructions is performed concurrently. The word concurrently is very important over here. If the result of I1 and I2 are dependent on each other, then the result of I1 may not be able to execute for the execution of I2. Unless and until you can perform any different operands like addition, and operator, or operator, XOR, subtraction, addition, you may operate any of the thing. But if it depends on the previous one, this data dependency conflicts may occur. What is the solution for that? You can avoid it by forwarding the directly feedback pipeline registers. For example, for execution, memory and memory, write and back, and all the results you can directly send it results to the arithmetic logic unit inputs. If forwarding hardware detects that previous arithmetic logic unit has written the register corresponding to the source for the current arithmetic logic unit, whatever the current arithmetic logic unit over there, current arithmetic logic unit, you can show it with the help of this red box. I have mentioned it over here in the given diagram. And control logic selects the forwarded results as the arithmetic logic unit inputs over there. This is all about the same example I have explained just now. Next is again, yes, there is one important part related to forwarding, generalized forwarding and and sometimes it is necessary to forward. First is we'll go with the generalized forwarding. It can pass a result directly to the functional unit that requires it, whatever that requires it, forward the result not only to the arithmetic logic unit inputs but also the other types of functional units. It can perform either when either the source or the destination operand of an instruction is not available at the expected time in the pipeline. The pipeline may get stalled. Such situation, we are aware about that. Such situation is called as the data hazard. Same thing that happened over here. For load or for store, it may definitely occur that hazard or generalized forwarding may able to do over there. Sometimes stall is necessary when related to forwarding that cannot be backward. Then, and that is the reason we are going with the stall. That means we have to go somewhere that we need to stay for a while unless and tend to for and waiting for the execution of the previous instruction in which you are completely dependent. This is all about the data hazard. And lastly, we'll go with that control hazard. What is that control hazard? Or I can say that branch difficulties. Majority of the time, this difficulty is occurred, which is faced when the branch and other instructions changes the contents of the program counter, where two different kinds of branches such as conditional and unconditional. If the conditional occurs, then it may go to the next, otherwise it may go to the previous one. So conditional branches may or may not cause branching, but an unconditional branch always cause branching. This difficulty is termed or is called as the control hazard, where the branches may or may not change the program counter to the other values other than PC plus 4, that is program counter plus 4. That can taken the branch such as changes the program counter to its target address, and untaken branch that can falls through as well. The program counter is not changed till the end of the instruction decode, where branch instruction, branch successor, instruction fetch, instruction decode, execution, and instruction fetch, and so that it can operate sequential manner. So we need to redo the instruction fetch. That can essentially a stall. If the branch is untaken, the stall is necessary. List the following. There are certain actions that need to be followed during the pipeline process, which helps in handling or which helps in to avoiding this particular branch hazard, where you can timely detect the branches detection of the branch instruction, or you can also go with the early calculation of branch addresses, and you may also go with the early testing of branch condition for such conditional branch instructions accordingly. If you follow all these steps, you may not have going to face this branch hazard like this. Four simple compile time schemes, that means freeze or flush the pipeline. You may directly hold or completely withdraw the whole pipeline. That can hold or delete any instructions after the branch till the branch DST is known. Branch instruction destination, unless and until the branch destination is known, you cannot do anything. You can do redo, or you can do redo instruction phrase without the first instruction fetch, or you can complete freeze the whole instruction in a given way, like this. Second one is you can predict it, the untaken one, which is simply treat every branch as untaken. When the branch is untaken, when the branch is untaken, the pipelining as if it has no hazards over there. It has no hazards over there. Third one is predicted untaken, where but if the branch is untaken, you can turn the fetch instruction into that is no operation, that is ideal way, and restart the instruction fetch as the branch target the address register. Instruction I plus 1, it requires ideal, and rest all others are ideal unless and until all the executions, sorry, all the remaining instruction counters may get fetched. You may not able to execute the next instruction. Branch target plus 1, branch target plus 2, and so on. Third one is predicted taken, that can simply treat every branch as a taken, not apply to the five-stage pipeline. Of course, we have till now seen all the five-stage pipeline over there that can apply the scenarios when branch target address is known before the branch outcome. Fourth one is delayed the branch. You can go with delay the branch execution after the next instruction. The pipeline sequence you may need to change, or branch instruction sequential successor and the branch target if taken. You can delay the slot to the next instruction. Then and only then the hazards may not occur, or branch conflict may not occur, or I can say branch difficulties may not occur to you. This is the simple example of delayed branch. You can simply delay the instruction unless and until untaken branch instruction and taken branch instruction. That may definitely help you to save the time, or that may definitely help you the to avoid from such hazards to you. The answer you can calculate it with the help of this particular formula. Unconditional it is 4%, conditional branch untaken that is 6%, and conditional branch taken that is 10%. The question arises: find the effective addition to the cost per instruction or cycle per instruction arising from every branch. The answer is like this: 0.04 multiplied by 2, 0.10 multiplied by 3, and for all branches it is 0.08 plus 0.30. And for the conclusion, I can say, I can definitely conclude in this particular manner, like pipelining promises the fast CPU by starting up the execution of one instruction before completing the previous one, and and second one is the class five-stage pipeline that can give you the risk, that can for the risk, that is instruction fetch, instruction decode, execution, memory, and write back. Along with that, pipeline hazards limit ideal pipeline structural or data control hazard that we have just now look at every single thing. In a simple way, I can simply summarize all the things that we have seen it in that video, where the use multiple independent data paths, that accepting several instructions that can read out at once, that means multiple instruction issue or superscalar. If overlap execution of several instruction may there, you can start with the next instruction before the previous one that has run to the completion, called as super pipelining. Pipelining in the student registration process or is like this: first is approval from the or authorities, then cashier, then registrar, and then student photo ID, and then pick up and then get executed. Or we can say that the laundry example that I have given at the start of the session is again be accepted over there. Next is in terms of hazards, as I have gone through all these hazards, control hazards or the instruction fetch unit of the CPU is wholly and solely responsible for providing a stream of instruction to the execution unit. The instruction fetch or in the instruction fetch by the fetch unit are in consecutive memory locations, and that's why they are executed. However, the problem arises when one of the instruction is a branching instruction to some other memory location. Thus, all the instruction fetch in a pipeline from consecutive memory locations are invalid now, and all those needs to removed unless and until you can go through the complete execution process. It is also called as the flushing of the pipeline. Instruction cache should be clear, register file should be clear, arithmetic logic unit should be clear, data cache should be clear, and then register file should be clear. Whole system, whole instructions may get flushed to enter it into the next set of pipeline. This can also induces a start till new instructions are again fetched from the memory or from the memory addresses that can specified in the branch instructions itself. Thus, at the time lost as a result of this, you can call a branch penalty. It can often dedicated hardware uh, is incorporate to fetch the unit to identify branch instructions, and we can able to compute the branch addresses as soon as possible and reducing the resulting delay by the result. Like this, you can alternate representation of a pipeline. Two abstract graphical representation of five stage pipeline is already given over there with the help of colors. First is yellow, second one is green, third one is orange, fourth one is I can say sky blue, third sixth one is purple, then pink, and then green. This is a drainage region where you can go with this particular technique. First is of task time diagram, and second one is space time diagram. Pipelining example for a photocopier, or we can go with the example of we can go with the example of that laundry. A photocopier with X sheet document, feeder copier is the first sheet, and so on. If this is a particular sequence of that execution, inserting bubbles into the pipeline that can cause various delays in the pipeline, where we'll go with a particular sequence, and the instruction fetch unit in the CPU is responsible for completely providing the stream of instruction to the execution unit. And it can, without data forwarding, these bubbles are needed to resolve the read after write data dependency. And two bubbles, if we assume that register can update and read from any one cycle, it can again be possible over there. Second type is of data dependency, where you can depend on the previous one, and the possible resolution through bubble insertion and data forwarding is given over here. Without data forwarding, the two or three bubbles are needed to resolve a read after load data dependency, so that you can execute all these things in a sequential manner again. The pipelining timing, or the pipeline timing performance that we have gone through, the total time required is called as the function unit, and the latching of results, you can divide it into three or four different parts as per the stages of the pipeline may consider. First, there may be various hazards that we have already discussed. The situation arises mainly when two instructions require a given hardware resource at the same time, and hence one of the instructions in the pipeline need to be stalled or need to be in that waiting position. The most common case is when the memory access at the same time by two instruction. Assume that one bubble may inserted due to read after load dependency, and after a branch when its delay slot cannot be filled. This is the simple formula for speed up. You can use that formula for execution. Next is these are the various examples that we have already gone through it at the session, while the session was going on. Next is optimal number of pipeline stages. Some assumptions are there. We always require some optimal amount of pipelines. While pipelines slice into queue stages, slice means we have divided it into various parts or various stages, like queue stages, and the stage overhead is, say, theta over there, and q by 2 bubbles per branch. This gives you the decision made midway. Fraction b of the instructions are taken branches. Average CPI, cycles per instruction, is equal to 1 plus bq by 2, and the throughput you can calculate it by using the given formula. Along with that, we will go with that given example. Meanwhile, U, V, W, X, and Y, these are the five different types or tasks that need to get executed with addition, subtraction, latency, multiplication latency, and division latency with addition, subtraction, multiplication, and division with 1 ns is there. Accordingly, throughput which will calculate with the original 1 divided by 25 multiplied by 10 to the power minus 9 is equal to 40 m computations or computations are possible. That may be the throughput for the given pipeline or given set of instruction. Next is pipeline performance can limits. The pipeline performance limited by data and control dependencies where hardware provision, data forwarding, and branch prediction can occur. In terms of software remedies, it can delete the branch, it can instructions ordering the branch, and instructions reordering also possible over there. Data dependencies and hazard that we have already gone through it, where data dependencies, data forwarding, pipelining, delayed branch and branch prediction, dealing with exceptions and avoiding pipeline is also there. When a previous instruction writes back a particular value computed by the arithmetic logic unit into the register, the data dependency can always be resolved through this forwarding approach. Pipelining control signals can also be possible over there. Third one is the summarized way. I can say like pipeline branch hazards can be compiler that inserts no operation after every branch, simple but wasteful. Branch is redefined to take effect after the instruction that follows it. Branch delay slots are filled with useful instructions via reordering, and mechanism similar to data hazard detector to flush the pipeline can definitely constitutes a rudimentary for a branch prediction that always predict that the branch is not taken, flush is mistaken, flush if mistaken. You can, if able to flush the completely clear all the instructions from the given data instruction set, and this may be the thing. Always predict that the branch will not be taken, or allow programmer to compile or compiler to supply the clues. You need to give the clues for at the time of prediction, and you can also able to apply the combination of factors or modern processors that use elaborate techniques to due to the deep pipelines. Where do we go from here? We can definitely able to assign the memory design. We can definitely be able to give the input and output at peripheral devices, input output programming, interfacing and interrupts, and to definitely to get the higher performance of the system. This is all about the pipelining and pipelining hazards process. Thank you for patience hearing. uh, Neeraj sir, over to you, sir.
Thank you, sir. So we are ending the session now. Um, the next session will be tomorrow at the same time. Thank you all.